In our last video, we looked at the basic structure of our carbohydrate monomers. Now, of course, as always, when we look at structure, one of our key goals is to use that structure in order to better understand the function, the properties, and the reactivity of our molecules. In the case of our carbohydrates, what we saw is that the basic structure of our carbohydrates is actually fairly simple. So we have this generic formula of CnH2ON for all of our carbohydrate monomers, which then results in we have a lot of carbons that have alcohols, right? So you can see the H2O right here attached to that single carbon. And then we have generally one carbon in each sugar that is a carbonyl. So you can see we have a single carbonyl carbon in each of these two sugar molecules here. Which of course these carbonyl carbons can act as either aldehydes or ketones, depending on where they're placed in our structure, resulting in two of our main different kinds of sugars, our aldoses versus our ketoses. So while our carbohydrates have a lot of complexity in terms of the number of different stereoisomers possible with all of these chiral centers here, they're relatively simple in terms of their actual organic functional groups. So a lot of our reactivity is going to be determined based on our ketone and aldehyde functional groups. Now, if you recall from organic chemistry, one of the key reactions of our aldehydes and our ketones is the formation of hemi-acetals and hemi-ketals. So this reaction relies on the electrophilic nature of our carbonyl carbon. So of course, our oxygen pulls electron density away from that carbon and creates a great electrophilic site for our nucleophiles to attack. This includes alcohols, which of course are another very common functional group in our carbohydrates. So our carbohydrates can react using our alcohols to attack our carbonyls, whether it's an aldehyde or a ketone, and we end up adding on that new alcohol to create a hemi-acetal or a hemi-ketal, depending on whether we have an aldehyde or a ketal, respectively. Now, again, of course, you should remember from organic chemistry that this reaction won't usually stop at our hemi-acetal or hemi-ketal state, but will react with a second alcohol to get a full acetal or full ketal. So notice how we've added on two different alcohols to what was originally our carbonyl carbon. That's the same both for our acetal and our ketal. The only difference is whether we have a hydrogen in the case of our acetal or another carbon chain in the case of our ketal here. So again, if our sugars have aldehydes and ketones, but they're also very rich in alcohols, we're going to expect to see this sort of addition reaction within our carbohydrates. So indeed, our carbohydrates are going to react those aldehydes and ketones with the alcohol groups on our sugars to create hemi-acetals and hemi-ketals, and this is going to allow our sugars to cyclize. So what is this cyclization of our monosaccharides? So again, within a given sugar, we have our carbonyl carbon, but we also have many different alcohol functional groups. Now, of course, a reaction doesn't just have to occur between two different molecules. It can also occur intramolecularly. And in fact, that intramolecular reaction is actually encouraged because our functional group is linked in such close proximity to our reactive functional group here of our aldehyde. So again, think of how proximity affected the rate of reactions when we were looking at our enzyme kinetics. So our alcohol down here can attack our aldehyde at the top of our molecule. That ends up creating this cyclized structure where now we have a bond between that fifth alcohol, or the alcohol in the fifth carbon rather, and our first carbon that used to be our carbonyl carbon. So at the completion of our reaction, we end up with this cyclic ring structure. Now, of course, we would also need a deprotonation event to remove our hydrogen here in order to eliminate the positive charge on our oxygen. So our final structure would just have our oxygen linked in that ring without any hydrogens here from what was our former alcohol functional group. Now, in addition to creating this new cyclic structure, we also end up creating a new chiral center. So once our alcohol attacks our carbonyl carbon here, our carbonyl carbon actually becomes a new chiral center, right? Notice that we have 4 unique groups attached here, since our ring is asymmetrical and one side of the ring looks different than the other side. This new chiral center we call our anomer, and so we would call this carbon specifically our anomeric carbon. So we end up with 2 possible stereoisomers, where we have our OH group pointing down with respect to the ring or pointing up with respect to the ring. These are marked as alpha and beta anomers. The alpha anomer is when we are trans with respect to our terminal carbon. So notice how our terminal carbon is pointing up and our OH group is pointing down. So alpha you can think of as trans, and for our beta then, of course, we would be cis, right? We're pointing up in the same direction as that terminal carbon. So not only does the cyclization change the shape of our sugar, but it also creates a little bit of extra complexity by adding on a new chiral center. Now, of course, since all of our sugars have alcohols and carbonyl functional groups, this sort of cyclization can occur for essentially any of our monosaccharides. So if we look at D-fructose here, we have a ketone, of course, instead of our aldehyde of glucose, but we can still do a very similar reaction, right? So if we take our alcohol here on our 5th carbon, we can attack that electrophilic carbon of our carbonyl, and we can cyclize our sugar. So again, you have the same sort of reaction, only in this case, of course, you're forming a hemi-ketal instead of your hemi-acetal, right? So notice that hemi-ketal right here, where we have our carbon bonded to 2 different oxygens, one oxygen that heads into the ring, which is the attacking alcohol, and of course, our carbonyl oxygen now becomes our new hydroxyl group. So again, this would be our anomeric carbon, and this would be the alpha form because we are trans with respect to that terminal CH2OH. Now notice in the case of our fructose here, our sugar ring does look a little bit different. And the reason for that, of course, is that our carbonyl carbon is now at the 2nd carbon instead of the 1st carbon. So our 1st carbon ends up hanging here off of our ring, and we get a 5-membered ring instead of a 6-membered ring. Now, of course, if you've ever seen the structure of DNA or RNA before, you might be familiar with the cyclized structure of ribose and deoxyribose. So we looked at the linear structure of D-ribose in our previous lecture. We saw that ribose has all of our alcohol groups on the right side in this R or D configuration. And of course, we can then cyclize that to create our ring structures, which is what you typically see in our DNA and RNA. Right? So you get these little rings that would then be attached together to create our DNA and RNA polymers. The only difference between our DNA and RNA is just this one change at our 2nd carbon. So we have a deoxyribose here for our DNA, where we remove that oxygen and just have our hydrogen here. So this is a modified sugar. We'll look at some other examples of modified sugars later, but this is one of the ways that we can increase the diversity of the functional groups in our sugars through these sorts of modifications. So essentially, all of our monosaccharides can cyclize through this sort of hemi-acetal or hemi-ketal reaction to form various ring structures. Based on the kind of ring that forms, we do have different names here for these structures. So our pyranoses are the 6-membered rings that form, and our furanoses are 5-membered rings that form from our cyclization reactions. These are named after pyran and furan, which are 2 different oxygen-containing ring structures that have a similar shape to our sugar cyclized ring structures. Now, of course, you might notice that within our sugar structures, we have, of course, alcohols on almost every carbon. So theoretically, we could react with any carbon and create a variety of different ring structures, but our 5- and 6-membered rings are most stable. So we'll tend to normally see only pyranoses and furanoses. So our 6-membered aldehydes will tend to form 6-membered rings. Our 5-membered aldoses or our 6-membered ketoses will tend to form 5-membered rings. And we generally won't see any larger or smaller rings commonly forming. By convention, the anomeric carbon is normally drawn on the right side of our ring structures. So we'll normally see that as our carbon over here at the right end. But of course, again, you can always pick out the anomeric carbon because the anomeric carbon will have 2 bonds to oxygen. So again, it starts off with 2 bonds as our carbonyl, and then when we attack with our alcohol, we end up with 2 bonds, 1 to the attacking alcohol and 1 to what was the oxygen of our carbonyl. So here we can see some of the different representations of our sugars as they cyclize. And of course, if we want, we can also include the pyran or furan in our names here to indicate the ring structure as well. So if you're looking at a ring sugar, you technically should include that pyranose or furanose name to indicate what size your ring is. But often we'll just refer to our cyclized glucose as just D-glucose because it can actually rearrange and go reversibly back and forth between our cyclized form and our linearized form. So we've added on 2 new kind of components to our name here, our alpha or beta indicating what anomer we have, and then our name here at the end indicating what kind of ring this is, whether it's a 6-membered or a 5-membered ring. Now, as I just mentioned, our sugars are not permanently linked into the cyclized form, right? So our acetyl and ketyl reactions are reversible reactions. You'll have actually an equilibrium where you can move back and forth between both structures. So because of that, our different anomers, while they are different stereoisomers, can actually be converted between each other relatively easily through this sort of reaction, right? We'd essentially just have to linearize it to some extent and then go back to our cyclized version. This sort of process we call a mutarotation. So this can happen with a base or acid catalyst. The process would look something like this, right? We just have to deprotonate our OH group, and then we can reprotonate it and create it on the opposite side. So we actually don't have to do a full linearization, then cyclization to switch which anomer we have. We can just kind of directly react with that and kind of eliminate the stereoisomer and then regenerate it to the new anomeric form. Of course, we can also do the same reaction with acid, which we've seen this, of course, in organic chemistry as well. If you're reacting with an acid first, you just end up protonating your oxygens first instead of attacking and then deprotonating, and then protonating rather. So you end up just switching the order of your mechanism. Now, again, one of the things that we learned in organic chemistry that's very helpful for looking at things like sugars is our polarimetry. So polarimetry, of course, enables us to look at optically active compounds or stereoisomers. through the use of polarized light. So if you remember, we have unpolarized light, of course, is what we typically see. It oscillates in all direction. And if we can filter it out so it's oscillating only in a single direction, we can then see how it interacts with our stereoisomers based on the angle of rotation of our polarized light. So again, we have this key law here where the rotation depends on the specific rotation, which is a constant for our given stereoisomer, depends on the concentration, and of course, the path length, the distance through the sample that it travels. Now, of course, for all of our sugars, since we have all those chiral centers and we have lots of different stereoisomers, they will all tend to be optically active. So polarimetry is a very useful method of analyzing sugars. You might remember, actually, we introduced polarimetry in organic chemistry by looking at sugar molecules. So if we wanted to track this sort of mutarotation process, where we're converting between our alpha and our beta form of our sugar, we can actually track this using polarimetry. So our two different stereoisomers, the alpha and the beta, will have different specific rotations. So you can see those noted in our table here. And if we add acid or base, we'll be able to react and convert between those. And we can see our optical rotation change over time as we react until we find an equilibrium mixture where we'll have some amount of each of our anomers depending on the relative stability of each of those different anomeric structures. Now, it's important to note that while these are fairly small changes, and they can, of course, switch between those two different anomers, it will still affect our behavior for that sugar, right? So you can't instantly convert from one anomer to the other. So you will still see a different effect depending on which anomer you have present. So most of our enzymes are actually specific for a single anomer. Again, of course, we know from our section on enzyme and protein structure that our enzyme will need to have a very specifically shaped binding site in order to fit our sugar. And so if you're switching which side of your ring that hydroxyl group is on, that switches where you're going to be able to form hydrogen bonds, and it can change how well that sugar will bind to our enzyme. So if you notice in our table over here, a lot of different enzymes will have a specific preference for a sugar based on what anomer it is, as well as what size of ring it is, right? So some will prefer the pyranose rings that have our 6 carbons, and others prefer the furanose rings with the 5-membered ring structure. So that sugar shape will influence the behavior, even if it's as small as our alpha or our beta anomer. So what will actually determine the preferred anomer of our sugars? Well, in order to understand this, we actually have to go back to our chair conformations that we learned in organic chemistry. So if you remember, whenever we have a ring structure, we can have these different chair and boat conformations based on how our atoms arrange themselves within our ring structure, right? So we have this sort of chair structure where we get kind of this wavy shape to our ring. So it kind of goes up on one end and then down on the other end. The boat structure would be kind of more like a U shape with it going up on both ends. In the chair structure, we're able to stagger our bonds in our large groups better to reduce our steric hindrance. With the boat structure, our conformation is more eclipsed and our groups are much closer to each other, and so it's much less stable. So we'll always tend to prefer our chair conformations. However, remember, we always have 2 unique chair conformations for any given cyclic structure. So here we have a beta D-glucopyranose, and notice we have 2 different conformations shown here. So this is the same structure, just drawn in 2 different ways. So we can draw it with this end up, or we can bend this end down and bend this end up, and we can create this other inverted chair structure. Again, of course, these structures can interconvert back and forth, but we can have a preference for one structure over the other. So in this case, the structure on the left will be more stable because it reduces the amount of steric crowding. So remember that when we have our groups pointing out to the side, these are our equatorial groups, and our equatorial groups have more space compared to our axial groups that stick straight up and down. So when we can put our larger hydroxyl groups pointing out to the side in this equatorial position, that reduces our steric hindrance again and makes our structure more stable. So notice how all of our hydroxyl groups are equatorial on the structure on the left, whereas they're all axial on the right, and we'll experience more of that crowding. So how does this relate to our anomers? Well, again, if we have an anomer, we're changing the relative position of our OH groups on our ring structure, right? So now in our alpha form, this is pointing down, whereas in our beta form, it's pointing up. So if you look at the anomeric carbon, again, that's our carbon right here with two oxygens connected. It's pointing down in one case and pointing up in the other anomer. So again, each of these can interconvert to get our two different chair structures. So here we have one chair structure on the left, and we can again bend it up and bend it down to shift between our two structures. Notice how all of our equatorial hydroxyl groups become axial, marked here with the brownish color, and our axial OH groups become equatorial. So our structure on the right has multiple OH groups as axial, and so it, of course, is less stable than our structure on the left. So again, notice we have our equilibrium strongly favoring the left structure of alpha-glucopyranose. Now, if we compare that most stable structure of alpha-glucopyranose with our most stable structure of beta-glucopyranose, you'll notice that here we have all of our OH groups equatorial, whereas with our alpha anomer, we have one group that's axial. So our beta anomer for glucose is going to be preferred over our alpha anomer, just based on the fact that we can form a better, more stable conformation with our beta anomer compared to our alpha anomer. So if we go back to our table here, showing the specific rotation of our different sugar anomers, so you'll notice that for our glucose, our equilibrium sits closer to our pure beta form than to our pure alpha form, right? So we have roughly 33 increase in rotation compared to our pure beta versus like over 60 compared to our pure alpha. So again, that's because our pure beta is somewhat more stable. So at equilibrium, we'll tend to have a bit more of that more stable compound compared to our slightly less stable alpha anomer. And we could do a similar analysis for our other sugars to explain why our equilibrium sits at that point between those two anomers. Each of it will be based on the preference or the relative stability and steric crowding within our anomer chair conformations. Now, of course, you might have noticed that within our sugar reactions, I've always stopped at the point of our hemi-acetal or our hemi-ketal, right? We react once and we create that cyclized structure, and then we just keep it within that hemi-acetal or hemi-ketal form in our cyclized structure. Again, in organic chemistry, we usually did not stop at our hemi-acetal or hemi-ketal, but we've continued to react with other alcohol functional groups. This will also occur for our sugar molecules. So for our sugar molecules, we have our hemi-acetal that can then react with other alcohols, Again, this would be a nucleophilic attack or a nucleophilic addition reaction onto our hemi-acetal to form our full acetal, where we have our carbon connected to now two different alcohol functional groups, including their carbon structures. And as you can see, what's happened here is I've reacted my hemi-acetal with another alcohol, is I was able to link two sugar molecules together. We call this a glycosidic bond, and this is going to be the key linkage that we'll use in order to bond our monosaccharides into larger sugar disaccharides or even large sugar polymers or polysaccharides. So we'll take a closer look at this reaction and the resulting larger sugar polymers in our future lectures.